All right, hello everyone. In this video, I got another heat conduction problem for you guys. We're transporting steam inside a pipe. So I have the problem statement and I have the figure as labeled as figure X. That's my cross-sectional view of the pipe. So pause the video for a second and give the problem a read. All right. Hoping you guys have given it a thorough read. So let's see. Steam is condensing. Okay, condensing. That means there's phase change, and phase change occurs at constant temperature. We know that. Inside a copper pipe, the inner wall of pipe may be assumed to be at a constant temperature of Tsat. All right. So the inner wall, as labeled here. Okay, as labeled in figure X. And R equals inner radius, R equals capital R sub I, T equals Tsat. Okay, that's the saturation temperature of steam. The outer wall, all right, let's go back here. The outer wall also remains constant at TW, T wall. So I have my two boundary conditions, one at the inner surface of the pipe and one at the outer surface of the pipe. The conductivity of the pipe may be assumed constant. All right, cool. Derive the steady state temperature profile in the copper pipe in terms of this, and this. All right, let's see what we got. Oh, and I'm sorry. We're also gonna need the inner and outer radius as the parameters. Okay. When we're deriving the profile, we're gonna be doing this problem symbolically, just algebra. We're not gonna plug in any numbers yet. So let's start off, shall we? So, okay, our assumptions. We have steady state, that's good. No change with respect to time, very nice. Constant conductivity, okay. Usually in some scenarios, conductivity is going to be a function of temperature. It's usually a Taylor series expansion, but we're just gonna K as a function of T is just equal to K, okay. We're assuming it's constant. Heat transfer only in the radial direction. If heat transfer is only in the radial direction, that means that there is no temperature change. Okay, hold up. That means that there cannot be any temperature change in the axial direction, and there cannot be any temperature change in the theta direction. Okay, that this second statement just doesn't make sense. Like, this is not, in a symmetrical pipe, this is not possible. Okay. So these are assumptions. Of course, let me just write the steady state assumption. That means that all the partial derivatives with respect to time are going to be 0. Okay, just to point that out. Now let's see. Let's start off with the heat conduction equation. Okay, rho Cp. So this is the heat conduction equation. Of course, we have constant density, constant heat capacity, but all of this is going to go away. Why? Steady state. Okay, at steady state, the entire left hand side goes to 0, and your vector notation, your heat conduction equation in the vector form, boils down to this. Very easy. The Laplacian of temperature is equal to 0. Okay, cool, nice, but what do I do with that? Well, that's simple. This is a pipe, this is a cylindrical pipe, so I'm going to be using the heat conduction equation in cylindrical coordinates. For pipe, it's going to be cylindrical. If I were dealing with a spherical ball, it would have been spherical. All right, and previously when we were dealing with plane, we were dealing with double pane windows, we had Cartesian. All right, so remember guys, we said heat transfer only in the radial direction, so there can only be temperature variation in the radial direction. Boom, boom. All right, our final governing equation, 0 equals 1R. Now partial derivatives have been replaced with total derivatives because T is just a function of R. T is just a function of radius. It's not a function of the axial length, and it's not a function of theta. Okay, all right. So now let's integrate this. All right. Upon integration, let's see what we get. All right, I'm just doing some, sorry about that. I'm just gonna get done with this real quick. So upon integrating once, you get C1 over R. Okay. All right. Let's just use different colors for our constants of integrations. All right. C1. And upon integrating twice, you get C1 times natural log of R plus the C2, which is the second constant of integration. All right, at this point we need to find C1 and C2, and for that we're going to be using boundary conditions. All right, use our boundary conditions. So we have two boundary conditions. Let me just rewrite that as shown in figure X above. Boundary condition 1, it states that at R equals inner radius, T is equal to T sat. Boundary condition 2 states that at R equals outer radius, T equals T sub W. So upon, like, when you use each of these boundary conditions, you're going to get two algebraic equations. Let's write that down. All right. Give me 1 second. C1 plus C2. Give me 1 second. Sorry. C1 plus C2. Let me zoom out a little. All right, let's zoom out a little. Sorry. Natural log RO is equal to TW, and natural log R, the inner radius, is equal to T sat. All right, I have my system of linear equations. So this is a 2x2 system. You can use linear algebra, Gaussian elimination, whatever you like. So I'm just going to be using elimination, and that's going to give me, let's see, equation 1, equation 2. If I subtract equation 1 from equation 2, I'll be left with, all right, let's see, let's hope I do not mess up the algebra. I'm subtracting the order of subtraction. Okay, I'm subtracting the top one from the bottom one. All right, please grab a pencil and paper and do the algebra with me. All right, RO, and this becomes equal to T sat minus TW. All right, we have our C1. Okay, good. We have our C1, and that's just the overall temperature difference. The overall temperature difference divided by the logarithm of the radii. Okay, the logarithm of the ratio of inner and outer radius. All right, cool. And using this result, you can just find C2. Just plug it back into either one of the above equations, either 1 or 2, and I believe you should get C2 is going to be, let's use the second equation. That's going to be T sat minus natural log inner radius times C1. This is where we substitute C1. Now we're just doing some algebra, guys. Now we're just grinding through the algebra. All right, we've already finished the heat transfer part. The transport phenomena were done. Now we're just doing the tedious part, the algebra, the symbolic manipulation. Okay. I mean, all right. I feel that most if you're in an exam condition, most professors are okay with this. At least in my experience, most professors are satisfied with once you give them C1 and C2, once you box those out, but some are not. So let's see if we can zoom out a little. Let's see if we can go back to our original expression. T equals C1 times natural log R plus C2. And now let's make substitutions of C1 and C2. That's let me use a different color. T equals C1. C1 is the overall difference, the overall temperature difference divided by the logarithm of the ratio. All right, don't miss my parentheses, times the natural log of, keep in mind R, lowercase r is my independent variable. Natural log R plus C2, and C2 comes out to be Tsat minus all this crap. All right. So I mean, once we have the temperature profile, we can find the location of the maximum temperature. We can find the average temperature. Okay, we can find the average temperature, etc., etc. But usually, okay, once we have the profile, this is my temperature profile, my overall temperature profile. We're usually interested in overall heat transfer. That's what usually a practicing engineer is concerned with, right? What is the overall heat transfer rate? What is the rate at which heat is escaping my pipe? And this seems like a brute force method. There's got to be an easier method, right? And well, guess what? There is. Remember, earlier we used a network of thermal resistances. We used the network analogy, the electrical circuits analogy, my bad. Network of thermal resistors. That's what we're gonna use next. Okay, network of thermal resistors. And the network of thermal resistors works well. Okay, this works very well if you're operating at steady state, and if your parameters like conductivity, density, etc., heat transfer coefficient are constant. Conductivity and heat transfer coefficients are constant. We haven't talked about heat transfer coefficients, but we will in the future. Heat transfer coefficients are constant. And in this scenario, the thermal resistors, the electrical circuits analogy is very powerful, are constant. Okay, so yeah, guys, this video was just a brute force method. We got what we wanted, right? And let's see. Yeah, this looks good enough. We have the temperature profile. We can plot it using Excel. We can plot it using MATLAB for different values of R, for different values of inner and outer radius, for different values of wall temperature, for different saturation temperatures. So yeah. But in the next video, we're gonna be a little more pragmatic. We're gonna be a little more practical and use a much more streamlined method, especially in the case of constant thermal conductivity. All right. Thank you so much for watching, guys. All right. Thank you. Bye-bye.